Before we start with the contents, I would first like to introduce our speaker today. It's Katharina Leu. She received her master's degree in applied geosciences in October last year after studying at the universities of Hanover and Aachen. And immediately afterwards, she started at LIAG in the rock physics and borehole geophysics working group. And this is a typical PhD position which has been approved by the DFG for 3 years. So that's about Katharina. And now a few words about the JET project, which Ms. Leu will introduce you to in a moment. JET is a project that runs within the framework of the ICDP, which means the International Continental Scientific Drilling Program. It is the continental counterpart to the probably better known IODP, which deals with drilling projects in the oceans, on the oceans. Yeah, I looked it up in my email. My first contact with JET was in January 2012. And the question is, why did it take almost 9 years to drill the borehole last autumn? And the original plan was to repeat the Mochas-Bohrung, drilled in 1969, to a depth of about 1900 meters on a campsite on the Welsh coast. And the original project name was therefore Mochas Revisited. So we want to drill the same borehole again. And we lost a year due to an environmental impact assessment. And the owners of the campsites are two brothers who had already witnessed the first drilling. And unfortunately, this assessment resulted, these brothers revoked their consent for the new drilling. So they realized what a burden such a borehole would be for their campsite. And as a result, the funding of about 5 million euros, already approved by the ICDP and by the NERC, that's the English pendant to the DFG, had to be reapplied. So that took some months, let's say years. And today we are talking about the Prees borehole and not about Mochas 2. And but that's not all that went wrong. The plan was for us to go to Prees in England with our equipment and carry out the borehole measurements. So our working group has great equipment for doing that. And unfortunately, because of COVID, it was not possible. So an English borehole measurement company has to be contracted to collect this data. And yeah, however, enough of the difficulties surrounding the project. Katharina will now present the first results we were able to obtain from the logging data. So, Katharina, the floor is yours.
Thank you for the introduction, Thomas. And thanks to everybody else for joining the LIAG seminar today. So as already announced, my presentation today will be about the first insights into analysis of geophysical borehole data of Prees-2 in England as part of the ICDP JET project. Continue? Or do I have to click for the marks? Okay. So first, a short outline of my talk, some words about the ICDP drilling project, about the early Jurassic time in general, the history of the Prees project, why Prees was chosen as a drill site, about the drilling progress, geophysical downhole logging, then we make a switch to astrochronology and cyclostratigraphy, and in the end, a short outlook to what will happen next. JET is the abbreviation for Early Jurassic Earth System and Timescale, and the main objective of this project is to produce a new global standard for the Early Jurassic, and this should contain an integrated stratigraphy and timescale. And the purpose for this is to answer questions about the long and short-term evolution of the Earth system, and these should later serve as comparators for present-day and future environmental transitions. The Early Jurassic lasted from about 200 million years to 175 million years ago, and comprises the Hettangian, Xenomurian, Pliensbeckian, and Toarcian stages. The Early Jurassic was a time of extreme environmental changes. So there are transitions from ice ages to super greenhouse events documented, including massive sea level changes and also mass extinctions. And what you can see here in the pictures is the constellations of the continents back then. So it was the time when the Atlantic Ocean was spreading and forming, and Pangaea, the continent on the left, was falling apart. And below, a reconstruction of life back then. So as you can see, it was the main time of the dinosaurs. And this is the area on which we will focus in the upcoming talk. This is today's northwestern Europe, especially England and France. And as you can see, this is the area where everything was coming together back then. It is the connection between the Tethys Ocean to the Arctic region via the Viking Corridor, and also had access to the Hispanic Corridor, and later to the Panthalassa Ocean when Pangaea fell apart. And this is a critical region, especially for floral and faunal analysis, so really good for biostratigraphy. And moreover, today it lies close to the global reference sections for the boundary of the Jurassic stages, so also favorable for stratigraphy. Now some words about the history that Thomas already told you a bit about. So there was already a borehole drilled into the early Jurassic in the 1960s in a place called Clanbedra or Mockras, which is located in the Cardigan Bay Basin at the Welsh coast. You can see it here in the right image. And this borehole showed a very thick succession of early Jurassic strata, including a lot of ammonites within a uniform mudstone, and very good conditions for biostratigraphy. And this is also what has been done to the core. So due to a lot of fossil sampling, the whole core was split up, and this led to today about 59% of the core left in the archives, and especially the lowest part of the Jurassic, so the Hettangian and Xenomurian stage, are missing today. And moreover, there were problems with the borehole back then, so there is not much geophysical data available. So the initial plan was to re-drill this Mockras core, but unfortunately this was not possible, as Thomas already mentioned, not only in terms of budget, but also because today Mockras lies in a conservational area. So a new drill site was needed, and this was found just 100 kilometers east of Mockras in the Cheshire Basin. And in this Cheshire Basin, there are two previously drilled boreholes called Wilkersley and Prees-2. Those are former oil exploration wells from the 1970s and 80s. And these also confirmed a lot of Jurassic strata and a lot of ammonites within it, so favorable conditions for biostratigraphy. Moreover, they showed a low thermal maturity, so that's because that's why those wells were dry. Yeah. This is another comparison of sites that have been considered to drill the early Jurassic. And as you can see, first of all, so the left picture is in a thickness scale, and the right picture is in a time scale. And what we have to look for are the stages. So especially the Hatangian and Xenomovian stages, because those are the ones that are missing for the Mokros core. Those are represented here by the violet and green parts. And as you can see, Mokros has the thickest succession of all these possible sites, but as already said, it was impossible to redrill this. And the second thickest succession shows Prees. And moreover, Prees can close these gaps for the Hatangian and Xenomovian stages, but also offer the opportunity to drill into the Triassic. And therefore, it would be able to establish a link to other ICDP projects that deal with the Triassic time. This is where the two boreholes are today. So Prees-1 is the borehole from the 1970s or 80s, and Prees-2 is the new borehole, so they are just on different sides of a road, not far apart. And the red line above marks the extension of these boreholes. Prees-1 was about 3.5 kilometers deep, whereas Prees-2 is just about 650 meters deep. Yeah, drilling went fine first until there was a major technical failure, as usual. And this lasted for about 10 days and led the project to run out of money for drilling. That's why it had to be stopped at about 650 meter depth and did not continue to 850 meters like initially planned. But still, the goals for the JET project could be reached. So the base Jurassic could be drilled, and also the transition into the Triassic. It's just the link to other Triassic ICDP projects that is unfortunately missing. On the right, this is the first picture of our core. And as you can see, it is a dark gray all-marine mudstone with a very high fossil content, so like already expected. So now, why do we use geophysical downhole logging and don't only look at the core and investigate the core? So the advantages of downhole logging are that we can measure the in situ conditions within the borehole, and we get a continuous data record, so we don't have to deal with split up cores. Moreover, we get a high accuracy depth measurement, so there is no bias due to core loss or whatever might happen to the core. Below, there are some examples of probes that are used to measure this borehole data. For example, the gamma radiation for measuring the radioactivity within the borehole, the electrical resistivity, or a caliper probe, which measures, for example, the size and shape of a borehole. And this is our borehole data from Prees. So on the left, you can see all the different parameters that have been drilled, like the spectral gamma ray density, porosity, resistivity, sonic velocity, temperature, and conductivity. And on the right, there is an image of the borehole wall. This is received by a so-called acoustic televiewer, and this tool is able to create a picture of the borehole wall by an acoustical measurement. And what you can see in this picture, these curved lines are actually fractures within the sediment made visible. So another advantage of downhole logging is that we can not only see a very large scale, like here the 650 meters at once, but we can also have a look at the sub-centimeter resolution with, for example, this acoustic televiewer. So now our first interpretations of these downhole logging data. This is a first interpretation to create a lithology log, so a prediction which kind of rocks occur within this borehole. You can see here a preliminary description of the core made by Steve Hasselbaugh and his team in England, who were present while drilling. And attached to it is our analysis for the lithology. This is made by cluster analysis. Cluster analysis is a method which divides the measurements of the observations into different groups that share common characteristics. So, for example, like what I've written in the brackets close to the cluster descriptions. For example, the combination of a high spectral gamma ray, a low sonic velocity, and a high porosity. This would form one cluster. And yeah, we were able to distinguish 4 different clusters. The first one for the upper part of the core, a second one that pervades almost the whole core, a third one that shows up in single intervals, and a fourth one for the lower part of the core. According to the description by observation and also to our, by looking at our data, we can confirm that cluster 3, that the orange part is a siltstone. And we can also confirm that the rest of the core description is mudstone. This also fits to our data, but we were able to distinguish 3 mudstones by our cluster analysis. These 3 mudstones have slight differences, but we cannot tell why, which are these differences. We assume that this might be due to a different content of, for example, carbonates or silt, because we know that there are these silt interlayers and that there are a lot of fossils inside, but by our current state of data, we cannot say which one is the mudstone that contains more carbonates and which one is the one with the silt and which one is the purest one. So that's our problem at the moment, but that should be fixed as soon as we get more data. Then there is this special looking part from about 450 to 580 meters. And in the core description, you can see that there are alternating layers. But this is more a sketch to say that there is alternation, but this does not represent the real order of alternation. And here we were also able to distinguish 3 different mudstones, but it's the same problem as before. We cannot say which one is the mudstone with the carbonates and which one is the one with the silt, or whatever might be the difference. Now we do a whole shift in topic towards astrochronology and cyclostratigraphy. This topic deals with the Earth's orbital and inclination cycles, called eccentricity, obliquity, and precession. Eccentricity is the change from a circular orbit of the Earth around the Sun to an elliptical orbit. This varies between 0 to 0.06, whereas 0 marks the circular orbit. And today we are at a value of about 0.016. And these cycles have, these movements have durations of about 400,000 years and 100,000 years. The next parameter is obliquity. This deals with the axial tilt of the Earth axis. This usually varies between 22.1 and 24.5 degrees and takes about 41,000 years time. And the last one is precession, and this refers to the rotational movement of the Earth axis. So you have to imagine this movement like a spinning top that is getting slower, or that you touched, and then it starts kind of wobbling. And this is the movement. And it takes about 19,000 years or 23,000 years time. this figure shows the same, just transformed into curves. And what you can see are the cycles that I mentioned before. You can see them in the peaks of these curves. So for example, in eccentricity, you can see a peak every 100,000 years. And if you have a look at the envelope of this curve, you can see that there is some regularity every 400,000 years. And this is also what is shown on the right side in the frequency analysis. This is just a conversion from the curves into the frequency domain, and these peaks mark the main detected cycles found in the data. And if we combine all these curves into one curve, what we get is the insolation. So the solar radiation that reaches the Earth's surface. And in this case, you can see the insolation at a 65-degree northern latitude on the 21st of June. And you can not only look about 1 million years into the past, but also about 1 million years into the future. And now you might ask, how do these different parameters affect the insolation on Earth? Eccentricity really has a minor effect of it of about 0.25%. It's just according to the Earth's position in the orbit and the distance to the Sun. Obliquity affects the latitudinal and seasonal distribution of the solar insolation. It has the same effect on both hemispheres. So just according to which hemisphere is tilted towards the Sun and away from the Sun. Precession has the same effect, but with an opposite effect on both hemispheres due to this wobbling movement. And talking about insolation, this leads us to the topic of paleoclimate. Especially ice ages, hyperthermals, and monsoons are controlled by the insolation on Earth. And therefore, these can be used as tools for reconstruction of the astronomical forcing in the past. And how this works is explained in the picture. So insolation leads to a climate response. This climate response might have a different fidelity or sensitivity to the insolation, but it is there. And this climate response affects the sedimentary systems. For example, due to temperature changes or wind patterns or water cycles. They affect, for example, transport, erosion, and weathering, and therefore grain size and clay mineral types, or whatever you can imagine. And these sedimentary systems are what we sample by drilling with our cores. And during drilling, geophysical measurements are made. And this is, in the end, our climate proxy data on which we have a look at. Another use of astrochronology and cyclostratigraphy is the use as a dating method. So it is possible to convert a stratigraphic depth series into a time series just by comparing or connecting cycles that are found in the proxy data to the past astronomical cycles. And here you can see the same picture as before. What is applied is a so-called time series analysis. This is comparable to a frequency analysis. So it shows a spectrum with peaks that suggest that a cycle with a specific frequency is present within the data. But in this image, you can see the perfect, beautiful case for this data analysis. And in reality, it looks a lot different. And this leads us to our data, which looks like this. So this is the most part of our core. the Hettangian stage, and also a part of the transition to the Retian, to the Triassic, and to the Sinemurian. Those borders are not really fixed. They are not exact, but we just assume them to be there. So we can say that this part that we are looking at has a length of about 100 meters in our core. So now, before applying any mathematical or computational analysis of this, I will show you a first attempt how to do this in an optical way. So this is the most part of what I've shown you before. So the last meters of the Hettangian stage. And again, the transition to the Triassic. Yeah, so what you can see are some blue brackets and some red brackets here. The blue brackets mark the 100,000 year eccentricity cycles, and the red brackets mark the 400,000 year eccentricity cycles. So now you might ask, how do we know where to put these cycles? So what we do for this is that we check the data for striking changes in amplitude, for example, within the curve. And then it's some counting and calculation involved, just by knowing that these peaks mark our smallest signal, so the precession signal of 20,000 years. And then you can calculate that 5 times 20 should be 100,000 year cycle, and for 100,000 year cycles should then mark a 400,000 year cycle. Yeah, but it's not that easy to say where these cycles start and where they end. Therefore, we look at the changes in amplitude, not only for the curve, but also for the envelope of the curve, for the 400,000 year cycles, for example. It's a lot of trial and error involved in doing this, and I will not go into further detail here because it might take too long and lead to confusion. Now we've done this for the whole Hettangian stage, and what you can see are that we can count 4 full eccentricity cycles and a 3/4 eccentricity cycle for these 100 meters of core. And with this information, we can calculate how much time is in this core part. And it's about 1.9 million years for our Hettangian stage here in Prees. This estimation quite nicely fits to other estimations in the literature, about 2.4 million years or 1.8 million years, for example, or something between 1.48 to 2.62 million years. And what we can do with this time information now is to calculate a sedimentation rate during this time. We know that we are looking at 100 meters of core and have 1.9 million years for it. So we can calculate a sedimentation rate of about 5.26 centimeters per 1,000 years. But this is just an average sedimentation rate for this stage. So as you already might have noticed, these brackets above, they have a different length in meters. They all represent 400,000 years, but comprise a different amount of meters within our core. And this marks a change of sedimentation rate during this interval. But to make it easier today, we will just stick to the average sedimentation rate. And this sedimentation rate can be used to calculate the period length of the cycles within our core. So what we've done in this table is that we just calculated how many meters comprise these 400,000 years in our core. For the 400,000 years, it's about 21 meters. For the 100, it's about 5 meters, 42 meters, and 21 meters. And now it gets a little more abstract or conceptual. So now we put the table into a diagram and plot periods, a period against depth. And if we assume that the period stays stays the same for the whole depth of the core, we would just get these lines for our different cycle durations. So far, so good. So this brings us to this. This is called a wavelet analysis, and this is now done by a computer. And it's nothing else than before. What you can see is period plotted against depth. And what we have to look in this picture are the red areas. This is where the computer is able to detect a clear signal. And just ignore this half round shaded part at the bottom. That's just to show that the calculation for the wavelet analysis is getting imprecise for these areas. And what we can do now is compare our optical analysis to the computer analysis. We can just superimpose it. And these vertical lines mark our transitions to the Sedimentary and to the Triassic. So our investigated area lies in between them. That's where we have to look at. And as you can see, our lines more or less lie on these red areas. So we were quite close to what the computer can see. And what else you can see, probably better when I change it back to this, is that between the 20,000 and 40,000 year cycles, the signal is turning to higher periods with increasing depth. So this red line has a slight tilt. And this is marking the sedimentation rate change that I mentioned before. So you can also see it in here. And then it's, of course, possible to correct these assumptions a bit. So here a factor of 0.9 was chosen to correct our optical assumptions to slightly smaller periods. But which factor should be used or should not be used depends a little bit on the eye of the beholder. So it could be 0.9 or 0.95 or maybe 1 point something. This is open for discussion. And yeah, this is already the end of my short introduction into astrochronology for you. I hope you could understand what it is used for. And now we come to the outlook about what will happen next in the project. So of course we want to improve our cluster analysis so that we can distinguish the three mudstones better. And therefore we would like to add more chemical data. But unfortunately, at the moment, the work in the lab for core scanning is paused due to the pandemic, so we have to wait a little longer to get this chemical data. Then we want to extend astrochronology by other downhole logging data. So we do not only want to have a look at the gamma ray, but also, for example, at porosity. And the astrochronology will be extended to the Sedimentary stage and also to the other Jurassic stages. And in the end, there should be a comparison to the Mokros core. Yeah, so far from my side today. I hope I could give you a first insight into the JET project and why we use geophysical downhole logging data and what astrochronology is and how it works.